Welcome to our deep dive into the world of semiconductor electronics. In this video, we'll explore the essential materials, devices, and simple circuits that form the backbone of modern electronics. From the basics of conductors and insulators to the fascinating properties of semiconductors, we'll break down complex concepts into easy-to-understand explanations. Whether you're a student, an enthusiast, or just curious about how your gadgets work, this journey will illuminate the invisible world powering our digital age. Let's begin by understanding the fundamental building blocks: conductors, insulators, and semiconductors. Let's define three key terms: conductors, insulators, and semiconductors. Conductors like copper allow electric current to flow easily due to their abundance of free electrons. Insulators such as rubber or glass resist the flow of electricity, making them perfect for protecting us from electric shocks. Semiconductors like silicon sit between these two extremes. They don't conduct electricity as freely as metals, but they're not as restrictive as insulator. This unique property makes semiconductors incredibly valuable in electronic devices, as their conductivity can be precisely controlled. Now let's talk about energy band theory, a concept that explains why materials behave as conductors, insulators, or semiconductors. In solids, electrons occupy specific energy levels grouped into bands. The two most important are the valence band, where electrons are bound to atoms, and the conduction band, where electrons are free to move. The gap between these bands, called the band gap, determines a material's electrical properties. Conductors have overlapping bands, insulators have wide gaps, and semiconductors have narrow gaps, allowing their conductivity to be manipulated. Intrinsic semiconductor is a pure form of semiconductor material, typically silicon or germanium, without any significant impurities. In this state, the number of electrons in holes, essentially the absence of an electron, are equal. At absolute zero, intrinsic semiconductors act as perfect insulators, but as temperature rises, some electrons gain enough energy to jump from the valence band to the conduction band, allowing a small current to flow. This natural behavior is the foundation for more advanced semiconductor technology. Extrinsic semiconductors are created by adding small amounts of impurities to intrinsic semiconductors, a process known as doping. This dramatically increases their conductivity. Depending on the type of impurity added, the semiconductor can become either N-type or P-type. This ability to control electrical properties is what makes semiconductors so versatile in electronic circuits, enabling the creation of diodes, transistors, and other essential components. Let's differentiate between N-type and P-type semiconductors. In N-type semiconductors, impurities add extra electrons, making electrons the majority charge carriers. In P-type semiconductors, impurities create more holes, so holes become the majority carriers. This distinction is crucial for building devices like diodes and transistors, as the interaction between N-type and P-type materials forms the basis of many electronic components. Doping is the process of intentionally adding impurities to a pure semiconductor to modify its electrical properties. By introducing atoms with more or fewer electrons than the host material, we can control the number of free charge carriers. This process is essential in the fabrication of all modern electronic devices, as it allows for precise control over how semiconductors conduct electricity. P-N junction is formed when P-type and N-type semiconductors are joined together. At the interface, electrons from the N-type region combine with holes from the P-type region, creating a depletion region where no free charge carriers exist. This junction is the heart of many semiconductor devices, including diodes and transistors, and is responsible for their unique electrical behavior. Depletion region is a zone around the p-n junction where mobile charge carriers are depleted. When the p-type and n-type materials come into contact, electrons and holes recombine near the junction, leaving behind charged ions. This region acts as an insulator, preventing current from flowing freely unless an external voltage is applied. The width of the depletion region plays a key role in the behavior of semiconductor devices. Area potential is the electric potential that develops across the depletion region of a p-n junction. This potential acts as a barrier to the movement of charge carriers, preventing electrons in the n-type region from moving into the p-type region and vice versa. Only when an external voltage is applied that exceeds this barrier can current flow across the junction. The barrier potential is a fundamental concept in understanding how diodes and other semiconductor devices operate. When a p-n junction diode is forward biased, the positive terminal of a battery is connected to the p-type side and the negative terminal to the n-type side. This reduces the width of the depletion region and lowers the barrier potential, allowing current to flow easily through the diode. Forward biasing is essential for the diode's conducting state, enabling it to act as a one-way valve for electric current in circuits. Reverse bias, the positive terminal is connected to the n-type side and the negative terminal to the p-type side. This increases the width of the depletion region and raises the barrier potential, effectively blocking the flow of current. Only a tiny leakage current flows due to minority carriers. This property is what makes diodes useful for controlling the direction of current in electronic circuits. Diode equation mathematically describes the current-voltage relationship in a p-n junction diode. It shows how the current through the diode depends exponentially on the applied voltage, with a small current in reverse bias and a rapidly increasing current in forward bias. This equation is fundamental for analyzing and designing circuits that use diodes, helping engineers predict device behavior under different conditions. Zener diode is a special type of diode designed to operate in the reverse breakdown region. Unlike regular diodes, Zener diodes can conduct in reverse once a specific voltage, known as the Zener voltage, is reached. This unique property makes them ideal for voltage regulation and protection circuits, ensuring that sensitive components are not damaged by voltage spikes. Zener diode's ability to maintain a constant voltage makes it an excellent voltage regulator. When connected in reverse bias across a load, the Zener diode allows current to flow once the supply voltage exceeds the Zener voltage, keeping the voltage across the load stable. This is crucial in power supplies and electronic circuits where voltage stability is essential for reliable operation. LED, or light-emitting diode, is a semiconductor device that emits light when an electric current passes through it. Unlike traditional bulbs, LEDs are highly efficient, long-lasting, and come in various colors. Their small size and low power consumption have made them the preferred choice for displays, indicators, and lighting in countless electronic devices. Working principle of an LED is based on electroluminescence. When a suitable voltage is applied in forward bias, electrons recombine with holes at the p-n junction, releasing energy in the form of photons, visible light. The color of the emitted light depends on the materials used in the LED. This simple yet powerful principle has revolutionized lighting and display technology worldwide. Photodiode is a semiconductor device that converts light into electrical current. It operates in reverse bias, where the flow of current increases when light falls on the junction. Photodiodes are highly sensitive and are used in a variety of applications, including light sensors, solar cells, and optical communication systems. Working of a photodiode relies on the photoelectric effect. When light photons strike the p-n junction, they provide enough energy to break electron-hole pairs, generating a current proportional to the intensity of the light. This property makes photodiodes ideal for detecting and measuring light in scientific instruments, cameras, and communication devices. Transistor is a semiconductor device used to amplify or switch electronic signals. It consists of 3 layers of semiconductor material, forming either an NPN or PNP structure. Transistors are the fundamental building blocks of modern electronics, enabling the creation of complex circuits, computers, and communication systems. Semiconductor devices are everywhere in modern electronics. They are used in computers, smartphones, televisions, and countless other gadgets. Diodes control current flow, transistors amplify signals, LEDs provide lighting, and photodiodes detect light. The versatility and reliability of semiconductor devices have revolutionized technology, making our lives more connected and convenient. From the moment you wake up and check your phone to the time you watch TV at night, semiconductors are at work. They power your alarm clock, enable your computer to process information, and even help regulate the temperature in your home. Their presence is so pervasive that it's hard to imagine modern life without them. Silicon is the most widely used material in semiconductor electronics. Its abundance, stability, and excellent electrical properties make it ideal for manufacturing integrated circuits and microchips. Silicon wafers are the foundation of the digital revolution, enabling the miniaturization and mass production of electronic devices. While silicon dominates the semiconductor industry, other materials like germanium and gallium arsenide are also important. Germanium was used in early transistors, while gallium arsenide is valued for its high-speed performance in specialized applications. The choice of material depends on the desired electrical and physical properties for each device. Integrated circuits, or ICs, are assemblies of multiple semiconductor devices on a single chip. They contain millions of transistors, diodes, and resistors, all working together to perform complex functions. ICs have made it possible to create powerful computers, smartphones, and countless other electronic devices that fit in the palm of your hand. Diodes are often used in simple circuits to control the direction of current. For example, they can protect sensitive components from voltage spikes or convert alternating current AC to direct current DC in power supplies. Understanding how diodes function in circuits is essential for anyone interested in electronics. Transistors can act as electronic switches, turning circuits on or off with a tiny input signal. This switching ability is the basis for digital logic, allowing computers to perform calculations and store information. The speed and reliability of transistors have enabled the rapid advancement of computing technology. Besides switching, transistors are widely used as amplifiers. They can increase the strength of weak electrical signals, making them essential in radios, audio equipment, and communication devices. Amplification is achieved by controlling a large current with a small input, a principle that underpins much of modern electronics. Logic gates are the building blocks of digital circuits, made possible by semiconductor devices like transistors. These gates perform basic logical operations such as and, or, and not, enabling computers to process information and make decisions. The integration of millions of logic gates on a single chip has revolutionized technology. Semiconductor devices are crucial in power electronics, which deals with the control and conversion of electrical power. Devices like power diodes, transistors, and thyristors are used in power supplies, motor drives, and renewable energy systems. Their efficiency and reliability have made modern power management possible. Optoelectronics is a field that combines optics and electronics, using semiconductor devices to generate, detect, or control light. LEDs, photodiodes, and laser diodes are key components in this field, enabling technologies like fiber optic communication, barcode scanners, and optical sensors. Microprocessors and microcontrollers are complex integrated circuits made from millions of semiconductor devices. Microprocessors serve as the brains of computers, while microcontrollers are used in embedded systems like washing machines, cars, and medical devices. Their versatility and power have transformed countless industries. Semiconductor devices are at the heart of many sensors and actuators. Sensors detect changes in the environment, such as light, temperature, or pressure, and convert them into electrical signals. Actuators use these signals to perform actions like turning on a motor or adjusting a display. Together, they enable automation and smart technology. Modern communication systems rely heavily on semiconductor devices. From mobile phones to the internet, transistors, diodes, and integrated circuits process and transmit information at incredible speeds. The miniaturization and efficiency of these devices have made global connectivity a reality. Semiconductor devices are the foundation of consumer electronics, from televisions and gaming consoles to smartwatches and home appliances. Their small size, low power consumption, and high performance have driven the explosion of electronic products that enrich our daily lives. Cars today are packed with semiconductor devices, controlling everything from engine performance to entertainment systems. Sensors monitor conditions, microcontrollers process data, and actuators adjust systems in real time. This integration has made vehicles safer, more efficient, and more enjoyable to drive. In healthcare, semiconductor devices are used in diagnostic equipment, patient monitors, and life-saving implants. Their precision and reliability are critical for accurate measurements and safe operation. Advances in semiconductor technology continue to improve medical care and patient outcomes. Factories and industrial plants use semiconductor devices to automate processes, control machinery, and monitor production. Programmable logic controllers, PLCs, and sensors ensure efficiency and safety while reducing human error. This automation has transformed manufacturing, making it faster and more reliable. Semiconductor devices play a vital role in renewable energy systems such as solar panels and wind turbines. Power electronics convert and manage energy efficiently while sensors monitor performance. These technologies are helping to create a more sustainable and eco-friendly future. The future of semiconductor electronics is bright, with ongoing research into new materials, faster devices, and more energy-efficient technologies. Innovations like quantum computing, flexible electronics, and advanced sensors promise to reshape industries and open up new possibilities for technology. Despite rapid progress, the semiconductor industry faces challenges such as material shortages, manufacturing complexity, and the need for constant innovation. Addressing these issues requires collaboration between scientists, engineers, and manufacturers to ensure a steady supply of advanced electronic devices. Production and disposal of semiconductor devices have environmental impacts, including energy consumption and electronic waste. Efforts are being made to develop greener manufacturing processes and promote recycling, ensuring that technological progress does not come at the expense of the planet. Solid understanding of semiconductor electronics opens up exciting career opportunities in engineering, research, and technology. As the demand for skilled professionals grows, educational programs and training in this field are more important than ever. The next generation of innovators will shape the future of electronics. Let's recap the key concepts we've covered: the nature of conductors, insulators, and semiconductors, the importance of energy band theory, the role of doping and p-n junctions, and the operation of essential devices like diodes, LEDs, and transistors. Understanding these fundamentals is crucial for anyone interested in electronics and technology. Semiconductor electronics have transformed the world, powering everything from smartphones to renewable energy systems. As technology continues to evolve, the importance of understanding these materials and devices will only grow. Stay curious and keep exploring the fascinating world of electronics. It's a journey that never ends.